Hi and welcome! In this video, we're going to introduce the concept of function composition. So our motivation here is that we want to be able to apply multiple functions. So we'd like to be able to apply one function to some inputs and then have another function apply afterward. Basically, we know how to do a function one time, but we'd like to then be able to apply another function to that result. So this is where compositions come in. So we say the composition of two functions, let's say they're called f and g, is written as the following. G composed with f of x, so that little circle indicates that we're composing the functions, and another way to write this would be g of f of x. So these are two different ways to write the same thing, and I often just say g of f of x, but sometimes I do say g composed with f, so you might hear both. Both really mean the same thing. So as you're listening to me, you heard me say g of f of x, but if you come back to this notation later, you might not be sure how to read it, so I just like to remind us that we read or say this as g of f of x, and we do this for either notation, so we read them the same. And what's important here is that we would do the inside function first, which is f, and then the outside function, which is g. So here I'm using f and g as our labels of our functions, but whatever the names of the functions are, you always do the inside function first, which happens to be f in this case, and then the outside function second, which happens to be g. So I think this order becomes more obvious if you look at the second notation, where we have f of x on the inside, and that's then becoming the new input for g. So I'll walk through that more, but this is the notation that to me really indicates that we do f first, so f gets applied to x, and then we apply g to that result. So our first notation where we have g circle f, the g composed with f, the reason why we often use this is because it really highlights that g composed with f is itself a function. So when we do one function and then another in a composition, we get another function, a new function, that is also a function. How many times can I say function? So when we have a composition, that composition is also a function, and its name would be g composed with f. So let's go back to our notation and talk a little bit about what happens and what order it occurs in. So what we're doing is starting with x. So x is our input, and in this case that we have g composed with f, x is the input of the function f. So we use x as the input to the first function, and that first function is on the inside, it's f. So we use x as the input, and then f maps that input to some output. That output would be f of x, we might call it y or something, but I'm just going to label it here as f of x. So we've given the function f an input, and now it's given us an output that is f of x. So this is the output of the function f. Now when we do a composition, we're now going to take this output and make it the input to another function. So we have the output, f of x, and this is now also the input of the function g. So f of x now becomes our input for g, and g provides us the corresponding output, which I'll say here is g of f of x. So this is the output of the function g. So we've done f, then g, and now we have our output. We started with x, and we ended with g of f of x. So an important thing to note here is that compositions require that the output of the first function is a valid input for the next function. So that output we got, that f of x, it has to be a valid input for the next function. So you might get an output that actually isn't in the domain of g, so we couldn't input it. So that's just an important nuance here, that we need this quality where the outputs of the first function are valid inputs to the second function. So this is one of the ways that function composition can actually get quite complicated, and we really don't need to worry about it too much. It's just important to note that not everything is going to work for a function composition, not everything's going to be able to be composed, but there are typically some adjustments we can make to make it work, or we just don't want to consider that composition if it doesn't work. But when everything works out and the functions can be composed, we can think of having the input x, that is the input of the function g composed with f, and then g composed with f, or g of f, takes that input and gives us the corresponding output, which would be g of f of x. Just know that when that composition is happening, there are two steps going on in between, where we have the first output of the first function that's then becoming the new input for the next function. So before we try these concepts out with any numerical or computational examples, I just want to try some conceptual examples to give us the idea of how this works with the inputs and outputs going together. So we'll do two examples that are based in some sort of word problem like scenarios that are applications of these concepts. So first, let's suppose we have two functions, f and g, and f is the function that takes an input of miles driven, and then it outputs the velocity in miles per hour. So what this function does, or like how it actually provides us this solution, we don't really care about right now. We just want to conceptually imagine that we have a function that has an input of miles and an output of miles per hour. Then let's say we also have a function g, where we input the velocity in miles per hour, and it outputs the gallons of gasoline used per mile. So this would be the gallons per mile. So we want to consider how we can compose these two functions. And we're going to look at them by considering the inputs and outputs, specifically the units of those inputs and outputs, and how they might go together. So if we first consider g composed with f, this means we do f first, f is the inside function, and then we do g. So we would start with the input to f. So if we use x as the variable, x would be in miles, since the function f takes an input of miles driven. Then we do f first, so f provides us an output that is miles per hour, so our f of x value has the units miles per hour. Now we've done our first function, and our hope is that we can then do the second function. So we want to apply g to this, and we'll see this is going to work great, because the inputs of g are also miles per hour. So we can do this, we can take the output of f, which is a value in miles per hour, and properly input it to g, which also is looking for a miles per hour. So we do g, and it provides us an output, which tells us the gallons per mile. So the overall function here, g composed with f, takes an input of miles and then tells us the corresponding gallons per mile. So it works. We can do g composed with f, and all of the units work out great. But we'll notice that this doesn't work quite so well if we go the other direction. So let's try f composed with g. This means we do f of g of x, so we do g first. When we do this, we're going to start with our input units, which is miles per hour, and then g takes that value and outputs the corresponding gallons per mile. Then we'd want to use this gallons per mile as the new input to the function f. So we did the first function, that was g. We did miles per hour and got an output of gallons per mile. And now we want to use this to input to f. But you'll see that it's not going to work because the inputs of f need to be miles. So we don't have a mile value, we have a gallons per mile. So f requires miles as an input, and we don't have that. So we would say that f composed with g, or f of g, is not defined. So this is a function composition that we cannot do in this context. Okay, let's consider another example just to close out. So let's suppose we have the function d, which takes an input of number of coffees sold and outputs the dollars in profit. Then let's suppose we have a function h, which takes an input of the number of hours a coffee shop has been open and outputs the corresponding number of coffees sold. So we have our two functions d and f, and let's figure out which way we can compose them. So we saw in the last example that only one of the compositions worked, and here we'll find the same thing. So just looking at these two functions, I'm noticing that the output of the function h corresponds to the input of the function d. So that number of coffees sold is what the two functions have in common. So we should be able to compose them as long as the output becomes the new input. So I would say the output of h matches the input of d, and so this means that d of h of x is valid. So this works, and so this means the function d composed with h is defined. So this would work by starting with h. We'd take the number of hours, then we would map that to the number of coffees. Then d would take the number of coffees and output the dollars in profit. So this works great. We start with the number of hours and we end up with the dollars in profit. But because this worked, this means the other composition won't. So the output of D does not match the input of H. So we can't do D first and then H because they don't match up. So if we did D at the beginning, like H of D of X, we would get an output of dollars in profit, and that's not a valid input for H. So we can't do H of D of X, and so H composed with D is not defined as a composition. So this is what this concept looks like when we use units or sort of a real-world scenario. What we need to just look at is the inputs and outputs that we know and just make sure that things are corresponding properly. So alright, that's it for this one. Thanks so much for watching, and I will talk to you in the next one.